before we start, I just need to mention that my first language is Afrikaans, so I will be speaking with a little bit of an accent. The second one is I live in the heart of the coal fields of South Africa, so I have a little bit of a bias towards coal. And the third one is that DMS cyclones, there's actually quite a lot to cover. So in half an hour's time, I won't be able to cover everything exactly. So let's see how it goes. The next half an hour, you are mine. And then if you behave yourselves, thereafter, I'll reward you with a small little comfort break. Okay, so today I won't be selling any cyclones. It's not in my mandate for today's session. So you can consider yourself lucky because I am considered ruthless when it comes to this. There will be no rocket science, no reinventing of the wheel, but I will, however, highlight to you the importance of checking your wheel's thread as well as the pressure every now and then. So looking at what we'll be looking at today is I will give you a condensed history of the modern dense medium cyclone. It's important to know where we come from so that we can appreciate that. And then I will also look into some of the factors influencing dense medium cyclone efficiency. And I've broadly categorized them under cyclone design, or characteristics, medium characteristics, and plant operation. With the Olympics being part of our recent past and still fresh in our minds, you'll see that a lot of my examples to explain some of the terms, I use Olympic examples. And then I'll close off with a little bit of a final word. Also have a look out for these green tables in my presentation, which will contain some very important parameters that you can use and should use in your plant. So let's kick off with our condensed history. So our story starts in 1858 with Henry Bessemer. Let me just get this rolling. With Henry Bessemer. Okay, so that wasn't awkward at all. So let's continue then. So as I'm trying to mention, our story started in 1858 with Henry Bessemer. Now, when his modeling career didn't take off for some reason as expected, he tried his hand at the dark art of science. And Henry's patent covered the use of chlorides of iron, manganese, barium, and calcium as a medium. But there wasn't really any serious industrial application until the 20th century. So then in 1891, a 43-year-old Eugene Bretney filed a patent for something which he called a water purifier, which, as you can see in the bottom left corner of your screen, is a very early ancestor of modern day cyclones, both hydrocyclones and DMS cyclones. And then in 1911, the chance process patent covered the use of sand and water as a medium in a cone separator. And in 1921, as indicated in the timeline, the first cone separator was commercially used in a plant using the chance process for cleaning anthracite. And then in 1922, there was experiments with magnetite as a medium to clean coal. And in 1937, the Tromp process was first to use magnetite commercially. So in 1940, which was a very good year, there was the first US ferrosilicon patent. And also in the same year, Destiny decided to intervene in the development of the DMS process, saying, yeah, listen here guys, you're going the wrong direction, let me help you out a little bit. So the Dutch State Mines was running a shallow bath dense medium plant in Holland for the cleaning of coal using a clay medium, which was then thickened in a cyclone. And this is where Destiny comes in. When the cyclone blocked, it was noticed that the overflow pipe was full of clean coal, suggesting that somehow the thickening cyclone was concentrating the coal. Now, this observation led to further investigation and ultimately the development of dense medium cyclones by the Dutch State Mines as we know it today. And then since the 1940s, mid-1940s, guys all over the globe have been starting using dense medium cyclones. So there in your bottom right is the original picture as depicted in the the Dutch State Mines Bible, which we refer to commonly. And then there on top is one of the very earliest plants, a coal plant, which incorporated the use of dense medium cyclones in coal processing. So the main evolution with regards to dense medium cyclones in the past 30, 40 years was in terms of the inlet design, the size of the cyclone, and the materials of construction. So let's delve a little bit deeper. As was mentioned by Ernst earlier as well, that for optimal performance in a dense medium cyclone, there's basically 4 groups of influences that has an influence on the performance of your dense medium cyclone. And I grouped them under cyclone design, ore characteristics, medium characteristics, and then obviously plant operation as well. So in this presentation under cyclone design, I will have a look at the physical cyclone ratios and dimensions and how they influence the operation of the cyclone. And then under ore characteristics, we'll have a look at a feed particle size distribution, as well as the washability specifically for coal and how it influenced the performance of your DMS cyclone. Under medium characteristics, we'll have a look at the effect of medium to ore ratios, as well as medium qualities. And then lastly, in plant operation, I'll delve a little bit deeper into feed head and then wear and maintenance around the cyclone. So if we kick off, for those of you who don't know, that's a dense medium cyclone installed in a coal plant at an angle. And one of the first parameters or dimensions that I want to mention is the cyclone diameter, or we also refer to the cyclone size. Now, this has an influence on the cyclone's total volumetric capacity. In other words, the maximum flow rate that you can push through the cyclone. And if we speak about the cyclone diameter of the cyclone size, we refer to the inner diameter, the wall-to-wall distance in the cylindrical part of your cyclone. And these days you get up to cyclones up to the size of 1.5 meters. So to give you an idea, these cyclones we inspect inside out is actually big enough that you can swim in it. And I normally get into it via the spigot. Well, after the corona lockdowns, I'm not sure there is many spigots I can fit through anymore. But let's leave it there. So inlet dimensions. Here I just need to clarify. If I speak about inlet dimensions, I'm not talking about this square to round or transformation piece connecting the round pipes to the rectangular inlet of the cyclone. I'm specifically referring to that rectangular or square inlet of the cyclone. And this is very important because this has an influence on the top size of particles that you can push through your cyclone. And normally we say your top size to your opening is 1 to 3. So what this basically means is that if you have an inlet with an opening dimension of 90 millimeters, square in this case, the 3 biggest particles that you can fit in that space is your top size particle that you can push through that cyclone. So in this specific example, for a 90 millimeter by 90 millimeter inlet, we're typically looking at a top size particle of 30 millimeters that you can push through there. Then we're also looking at the vortex finder diameter, and this has an influence on the maximum capacity going to your overflow. There's one of these big cyclones which I inspected inside out, and if I refer to the vortex finder diameter, I'm referring to the inner diameter as indicated by the red arrow on the slide over there. And then we also need to consider the spigot diameter, which is also quite important because this has an influence on the maximum capacity, the underflow of your cyclone. It's quite important to have a look at your spigot every now and then or whenever you get an opportunity, because you get instances where you get some interesting stuff stuck in that spigot which can mess up the whole performance of your cyclone. I want to say, even one of the most important ratios that you need to consider when it comes to cyclone dimensions is your spigot to vortex finder ratio. I'll speak a little bit later on in the presentation more on this, but just to give you an idea, on your x-axis, there you have your spigot to vortex finder ratio, and on your y-axis, your EPM, which is a value for efficiency of separation of your DMS cyclone. So remember here, the lower your EPM, the better, because the better your efficiency is. And you can see from 0.8, that means your spigot ID is about 80% of your vortex finder ID. You get a sharp increase in your EPM values. So we as a cyclone OEM suggest that you never allow your spigot to wear past 85% of your vortex finder ID. All right, so let's have a look at a summary of some of these parameters I just had a look at, and we compare it to what the guys originally did in a few decades ago with the Dutch state mines. So typically then the cyclone diameters available was anything from a 200 millimeter to a 750 millimeter. And as I mentioned, these days you get huge monsters up to 1.5 meters in diameter. So inlet dimensions, orangely, everything is referred to the cyclone's diameter as a reference. So the Dutch state mines refer to 20% of the cyclone diameter. These days you get anything between 20 and 30%. Your vortex finder diameter as a ratio of your cyclone diameter, 43%. And once again, today there's a little bit of variability, anything from 42 to 50% of your cyclone diameter. And then very important, the Dutch state mines already noticed it, that your maximum spigot ID should not exceed 85% of your vortex finder ID. And that's why these days, depending on the application, our spigots are sized anything between 70 and 80% of the vortex finder that was selected for that specific cyclone. So from hand-drawn sketches to very sophisticated mathematical and CFD models, the DMS cyclone has come very long and a very far way to this elegant, reliable, and effective piece of equipment that we know and trust today. And I think it's important that we take note of it and respect it when we walk past it next time in the plant. So a little bit of a bonus fact. So most of you may have noticed that classification cyclones are typically installed upright or vertically, and then DMS cyclones is installed at an angle near horizontal position. Now the reason for this is, if you were to install your DMS cyclone vertically, you will get that gravity will work in the direction of your spigot. And this will pull the media down, which is heavy, down to your spigot and cause some sort of slumping effect around the spigot. And the effect of this is that it will pinch your inner air core, which is detrimental to the efficiency of your cyclone. So separation efficiency will be very sensitive to inlet pressure and medium viscosity. On the other hand, if we install it at an inclined position, you'll see that the piping is easier, there's not as much headroom available, so the installation is easier as well. But also, your cyclone then buffers a lot of the variations in your feed much better, because your spigot is a little bigger, your inner air core is a little bit bigger and more stable as well. So you get an effect that even though there may be some variations in your feed, your product coming out of your DMS cyclone is relatively constant. So here to just give you a quick indication, if you were to install your cyclone exactly horizontal to your floor and you have to stop the cyclone for some reason, you'll find that the material inside the cyclone will not be able to drain. It will move back to your head or to your inlet head. If you install it at a 10 degree, for instance, because we know that DMS cyclones is 20 degree cone angles. So if you install it at a 10 degree, you'll find that should the cyclone stop, the material will also stop just in your cyclone and it won't drain out. So that's why typically when we install DMS cyclones, we install it at about 15 degrees to the horizontal. And the plain simple reason for this is when your cyclone has to stop, the material can drain out of your cyclone. Now, as an example, we are picture people, so let me show you some pictures. There's the inside of a diamond cyclone in this case, where it's installed correctly, and you can see when the cyclone is shut down, it drains out and everything is fine. On the other hand, if it's not installed correctly, you can see that there's some trouble inside the cyclone. Now, those of you who haven't worked with Fezzi or with magnetite before, if that stuff gets hard and dry, it's like cement. So cleaning out this cyclone is a terrible demeanor, and it's not very nice to do. So just to give you an indication, there I zoom in a little bit in your vortex finder, and you can see even up to the vortex finder, there's a lot of medium that is going to be cemented basically in that vortex finder now. All right, so for the next part, I need you to focus very hard, breathe deeply. We're going to do some mathematics, but I'm going to take you slowly, step for step through this, and we should come out of it fine. So each and every particle passing through a cyclone, there's basically two main forces acting on these particles. The centrifugal force, indicated by the red FC there on your left, pulling the particles to the outside wall of your cyclone, and then the drag force, pulling your particles to the inner core of your cyclone. So if we look at the definitions or formulas, so there's a formula for centrifugal force and your formula for your drag force. So if we manipulate a little bit and we get a formula that's a little bit more palatable, we see that your M, which will be your mass, stands across your density of your liquid, the area of your particle, and the radius of the motion that the particle will follow. So for this example, let's say we assume that we have perfect spherical particles. So we know how to calculate the surface area, we know how to calculate the volume, and because it's perfectly spherical, the constant is 0.5. So let's plug this in. First of all, we need to know that mass equals volume times density. So the mass of your particle will then be that area of your particle times the density of your particle. All right, keep that in mind. So plugging volume and surface area into our original formula, and there's the original formula on the top right, and now we plug in our spherical details. We replace mass here with volume times density. We get this long formula. We manipulate it a little bit again. You can have a look at it afterwards. We remove pi times by 3/4, and then we get something to this. So now at this stage you can breathe. That's done with the mathematics. I just want you to focus on that formula blinking on your screen right now. So let's see what we're going to do with this. Remember the left hand still representing your centrifugal force, taking your particles to your spigots, and the right hand focusing on your drag force, taking your particles to your overflow. So let's say we have bigger particles. There's that formula we calculated. So if we look at bigger particles, it means the radius of the particle will increase. So now you have a higher centrifugal force. So now there's a higher tendency for your bigger particles to report to your underflow. If we have a look at heavier particles, so that means the density of your particle increases. Once again, your centrifugal force increases, and therefore there's a higher density to report to the underflow again. And then also heavier liquid, typically in DMS applications. So if you increase the density of the liquid, now you have a higher drag force. So there's a higher tendency of particles to report to your overflow. And then similar for your cyclone diameter, if you increase that, higher drag force, higher tendency to send more particles to the overflow. Now, this is very, very important to understand before you can have a look at the next graph that I'm going to show you. So here's a graph showing particle sizes on your x-axis and then EPMs, or a measure of efficiency, on your y-axis. Remember, the higher the EPM, the worse it is. So you want as low as possible EPMs for good efficiency. Now there's different colored graphs over there representing different cyclone diameters. And you can see that all the cyclones give a similar efficiency here at the bigger particles, but then one by one, they start to veer off. And that point where they start to veer off and you see an increase in the EPM or a decrease in the efficiency is what we call the breakaway size. And that's why it's important to have an idea of the PSD, or the particle size distribution, that you're going to feed into your cyclone, because you want the portion of your feed going to your specific cyclone to be that portion smaller than the cyclone's breakaway size, to be as little as possible, to give your cyclone the best opportunity to give its best performance. So there is a graph showing your cyclone diameters at the bottom axis and the breakaway size on the y-axis. There's a simple formula you can have a look at to try and calculate it. Important here is that your cyclone, if we look, for example, at 1150 cyclone. 1150 cyclone, the breakaway size is 6.28 millimeters. It will still, however, be able to separate a 5 millimeter particle, but not as efficiently as the bigger particles anymore. So keep that in mind. So moving on, I'm going to have a look at feed washability. Remember, I said I'm biased towards coal. So if we talk about washability, here I'm going to explain how it happens in the lab. So they make up a certain medium at a certain density. And for this, they typically use something like zinc chloride solution, which is a little bit corrosive. So they only use it in the lab conditions. And then they make up different densities. So you take your sample and then you start to float and sink it. Put it in each density fraction. And as you go along, it will separate. Some of the stuff will start to float. Some of the stuff will sink. And then afterwards, you take each of these separate portions and you analyze it for whatever quality you're interested in. And then you'll get something like this, which we call a washability graph. So the purple line here indicates your yield. So as the density increases, you can see your yield will increase as well. And you read the value here on the primary y-axis. And then as your density increases, your ash will also increase, right? And you read your ash value, for example, here on the secondary y-axis. So as an example, if we want to wash for a coal at a density of 15%, we'll see that we'll have to cut at about 1.58 density. And at a density of 1.58, we can expect a yield in the order of 72%. So very important information that's gathered in your washability data. Right, let's look at your medium characteristics, and then we kick off with your medium to ore ratios. So for any cyclone to work efficiently, there needs to be a certain amount of ore and a certain amount of medium present in that cyclone. So for efficient separation of the ore particles, one requires a certain volume of medium. Remember, if we talk about medium to ore ratios, it's in terms of volume, and then a volume of ore being fed to the cyclone. If your medium to ore ratio is too low, you'll get a situation where there's overcrowding of solids, loss of efficiency, etc. If your medium to ore ratio is too high, you get an increase in equipment size, higher operating costs, increase in medium losses, and very little effect in terms of improvement of efficiency. So at the upper end of the range, above 5:1, the efficiency of separation becomes very good at the expense of capacity. So let's have a look at some figures, coming back to the Olympics again. So if we look at this swimmer, and we say the swimmer represents the ore particle, and then the water in the swimming pool represents the medium. Which of these three situations do you think is ideal for these swimmers? All right, so let me help you. The one on the right, you can see there's just the medium to ore ratio is too low. There's too much ore for the medium in that swimming pool. On the left, that swimmer will have a golden opportunity to break the Olympic record, but your swimming pool is too big. There's no need for that swimming pool to be this big. So your medium to ore ratio is too high. So the ideal is the one here in the middle. Everyone has their lane. Swimmer to swimmer interaction is at a minimum, and everyone get an opportunity to do what they need to do best. So here's one of those green tables. In coal, we're typically looking at 3.5 to 4.5 to 1. This means for every 1 cube of coal ore that you wash, you will need at least 3.5 cubes of medium. Medium being your mixture between magnetite and water. And there's the rest for diamonds and then some other minerals as well. So quickly look at medium suspensions. There's two types. We get the homogeneous and the heterogeneous medium suspensions. Homogeneous, we're typically looking at organic liquids and salt solutions. The only issue with this is that the organic liquids tends to be carcinogenic, and then the salts tends to be corrosive. So these are only used under very regular circumstances in a lab situation. So what we like is the heterogeneous setup, where we look at water and solids. And these solids, we saw it can be sand, galena, or whatever, but these days the majority is magnetite, specifically for coal, and then ferrosilicon or Fezzi for the rest. So if we look at medium qualities, one thing that we need to know is that before your DMS cyclone is a DMS cyclone, it's actually a classification cyclone. So you will get classification of your medium particles inside your cyclone, where you get, for example, a feed density of 2.65. The overflow will be something less. The underflow will be something higher. And very important to note, however, that your cut density will be there somewhere a third from the bottom of your cyclone. So how do we measure whether our medium is actually healthy and contributing to the efficiency of our cyclone? We have a look at the differentials, the density differentials. And the one specifically used most often is your feed to overflow differential, which needs to be between 3 and 12%. So you calculate this by taking the difference of the feed and overflow medium density, and you calculate it as a percentage of your feed density. And you can see in this specific example, 7.55 falls smack bang in the middle of the 3 and 12%. So you are okay and you can go on. So let's typically see what happens inside a cyclone, what should happen inside a cyclone. So here is the small circle representing the spigot of the cyclone and the big circle representing the vortex finder of the cyclone. We're looking at the cyclone from the top. So as you feed a certain medium into the cyclone, we'll start to see that there's segregation and we get some density bands. And they're just fictive numbers that I included over there. Your lightest band will be for this example, 1.2 near the center of the cyclone, and then the higher densities will be on the outside. Important to note is that there will be a certain area where you have a locus of 0 vertical velocity. All right, everything inside that red circle will report to your overflow, and everything outside that circle will report to your spigot. And they are indicated as well on the left. So let's say we have a particle with a density of 1.9, which is typically discard in a coal sense. It will find its way where it feels comfortable between the 1.8 and 2 density bands, and it will report to your spigot. Nice. If we have a nice piece of coal, 1.3, it will migrate and it will fall within the locus of 0 vertical velocity and report to your overflow. Perfect. This is what we want. So what happens if our differential is too high or our medium is unstable? This means that you will get classification of your medium. And as you can see, the numbers of the density bands change now. And the effect will not be so much on your discard, for example, in coal, but look at what happens to a coal particle. Instead of reporting to your overflow, it will now report to your underflow. And there goes your profit. Goodbye. Okay, so here's an interesting graph that you can use to check whether your medium used in your DMS cyclone is healthy or not, with circulating medium on your x-axis and then your overflow density on your y-axis. There's your acceptable range, falling between 3 and 12%. Above it, you'll sit with high viscosity, and below it, you'll sit with low stability. So let's say, for example, you have a feed density of 1.65, and an overflow density of 1.64. You'll see you'll fall outside the acceptable operating range, and you'll sit with high viscosity. If you sit with a 1.85 feed density and a 1.5 overflow density, your medium is unstable. All right, so you're basically sitting here with a glorified water feature in your plant. But if you sit at a feed density of 1.55 as an example, and an overflow density of 1.4, you are within range. Let's talk about medium a little bit further. Now, just like in the Olympics, that you get different athletes for the different sports, there are different types of medium required for the different work that they need to do. So starting off with FeSi or ferrosilicon, particle shape is a result of the production process. Now, milled ferrosilicon particles are angular in shape, and water atomized produces particles that are of a spherical nature. But even better than that, the gas atomization produces highly spherical particles. An example of the three particle shapes are shown here on the left. On the magnetite side, it's normally in terms of the PSD, so you get your fine grade, your medium grade, and your coarse grade, and they are indicating in brackets what this is referring to. Moving over to plant operation, feed heads specifically. Now, as you know, that the feed head to a dense medium cyclone is normally referred to as some sort of relationship to the cyclone's inlet diameter. Now, there's a few formulas that we can have a look at, but let's have a look quickly. There's Bernoulli's formula. This may seem familiar to you. We had a look at our centrifugal force as well, but now instead of radius, let's just change that radius and we refer to the diameter of the cyclone. So if we combine these two, we get something looking like this, where K is just a constant, looking at gravity and your discharge coefficient. And then you can see there's the mass of the particle, the head, and the diameter of your cyclone. So this is now a nice way of sort of normalizing the main force acting on each and every particle going into your cyclone. So now you can talk about it in terms of the force acting on each and every particle, independent of what the diameter of the cyclone is. So let's have a look at this one. Coming back to the Olympics again. This is Joe Kovacs, American shot put athlete, and he agreed to play model for this presentation today. So let's say that's your ore particle. Each and every ore particle needs a certain energy to get displaced to where it needs to be. So different ores will require different feed heads. And there's an example of calculating at what pressure the cyclone should operate at in a coal setup. So let's say your feed density is 1.55, gravity, while we're still working here on Earth, 9.81, and a head of 9D. And this cyclone is an 800 mole cyclone. There you can see 110 kPa at least. By manipulating that formula, you can easily see how to calculate the head of your cyclone as well. Don't go below 7D, since this will have an influence on your air core and it will become unstable and your performance is out of the window. So once again, there's the typical parameters: coal at 9D, diamonds at 12 to 15, and then there's a whole lot of other minerals, and that ranges between 12 and 20D. Just be careful. You can't go now and increase your feed pressure as much as possible, because there's an exponential relationship between your relative pressure and your relative wear rate. So your efficiency will be good for 2 days, and then you need to replace your whole cyclone. So there's a nice balance, and that's why you need to take into consideration that previous green table I showed you. Wear and maintenance. So the wear in a dense medium cyclone is essentially because of the particles bumping into the walls of the cyclone. So here I have some examples. There's some typically wavy patterns that we see in a tiled DMS cyclone, and then extreme cases where you have some tramp metal passing through. You can see tiles cracking and then starting to fall out in the path of the path of the motion of the particle. So we also know that the higher wear rates can be expected at the bottom third of the cyclone as the heavier or bigger particles get pushed together, condensed in a smaller space, as well as the outer wall of your vortex finder. So it's important to inspect these from time to time. As you can see there on the left, you can see that spigot had some rough times. And then on the right, the vortex finder, you can see on the outside there's some extensive wear. Once again, this graph I showed you earlier, when you inspect your spigots, make sure that it doesn't exceed 85% of your vortex finder ID. All right, further on wear and maintenance, specifically on tiled cyclones now for this example, very similar to dentistry. What is it that you need to look at? You need to watch out for gaps between tiles. You need to watch out for missing tiles. You need to look out for cracked or broken tiles. And not only on brand new cyclones, but also in terms of refurbishments as well. Be careful to use backyard mechanics to do your refurbishments. Don't learn the hard way the meaning of penny wise, pound foolish. Today's saving of 100 Rand will cost you 1,000 Rand next month. As a simple example, just the different types of tiles that can be used in a cyclone. Your normal square tiles on your left and your engineering tiles on your right. If we tile a cyclone with these different tiles, maybe you can already see the difference, but as time passes on, we'll know the tiles wears through. Now, look at the gaps between the tiles. All right. So what is this? So what? Let's have a look at wear over time. So on the right-hand side with the engineered tiles, the wear is relatively constant because the space between the tiles stays relatively constant. But the wear on the red tile or the standard tile increases as the gap between the tile increases. Still, what does this matter? I've already spoken about that 85% now, so there's a certain cutoff point, and you can see the red example will reach that cutoff point much quicker than the green example. Also important to note, preventative maintenance, very important, but how much is enough? So as we move on the graph from left to right, an increase in preventative maintenance, and we know the more preventative maintenance you do, the less corrective maintenance you have to do. But the game here and the goal here is to try and balance it out because you have a total maintenance cost as well. And this is where your OEMs needs to assist you. The idea is to get into that optimal maintenance zone. To the left of it, insufficient preventative maintenance. To the right, excessive preventative maintenance. All right, so let's get to the last couple of slides. So we saw that DMC efficiency rests heavily on your ore characteristics, your operation, your DMC design, as well as your medium. You may think that you sit like a nice on your chair, everything is fine. You may be neglecting one of these items, and this can have catastrophic.
For proper engagement is actually after the tabling of the.
All right, so don't get caught out. Focus on all four of these factors, and you should be okay. As I mentioned, sorry for the technical difficulties in the beginning. There's a lot of stuff still to cover on DMS cyclones specifically. My contacts will be available afterwards, so you're more than welcome to contact me. It was an absolute pleasure presenting to you today. I hope you enjoyed it as much as I did, and I could shed a little bit of light on the wonderful piece of technology that we call DMS cyclones. Thank you.